Our next speaker is Steve Fox, and his title is Brain Synchrony and Oscillation.
Thank you, John, for that very nice introduction to what I'm going to say. I have to apologize. I have a slow brain. My excuse for that is I grew up in West Michigan farm country. My mouth works much faster than my brain. This gets me in trouble. The point here is that I'm going to read this talk. But if I left it up to my brain, I'd never get done in 8 minutes. The job of the hippocampal formation appears to be forming memories to help us predict the results of our possible future actions. Hippocampal formation is a loop. Adrenal cortex, subicular cortex, CA1 and CA3 that forms the hippocampus proper, and the dentate gyrus. The neocortex sends highly digested sensory information into entorhinal cortex, and it's further synaptically processed around the hippocampal formation loop, which generates many parallel loops of overlapping cell assemblies in the hippocampal formation. By repeated synaptic strengthening, the cell assemblies become a stable representation of map of the environment. When incoming sensory information disagrees with the map, then exploration is triggered to repair the map. Exploration is associated with theta frequency oscillation at 4 to 10 hertz, paced by the medial septal nucleus. Its cholinergic and GABAergic neurons fire faster and rhythmically during theta, and they project these hippocampal formation areas. The theta activity has both tonic and phasic effects that improve memory formation. The tonic effect is a muscarinic, cholinergic increase in the excitability of both projection cells, for example, O'Keefe's place cells, and interneurons, Jim Ronk's theta cells. An increase in the excitability of both the projection cells and the interneurons. It's producing a generalized inhibition in a case where we've got increased excitability of the projection cells. This theta state of the hippocampal formation increases the signal-to-noise ratio of place cells, enhancing the location signal, so improving the synaptic strengthening process. The oscillatory effects of the theta include rhythmic activity of the GABAergic septohippocampal neurons, which phasically inhibit the hippocampal interneurons. This phasically disinhibits the projection cells. So that the projecting cells also fire phasically. The slow theta synchrony modulates high-frequency oscillations, gamma, improving communication between regions and increasing the probability of the proximity of neuronal activation required for synaptic strengthening. By applying various drugs to the medial septum, Kevin Bolden showed that the tonic component of theta is sufficient for forming the representation of the context, but that the oscillatory part was necessary for its use in behavior. Now I'd like to talk about some current data from Ben Tesler. He enhances theta activity by transcranial electrical stimulation through the skull. Even in the rat, the hippocampus is deep in brain. Here it is. Ben's model here show that standard methods for transcranial electrical stimulation, just passing sine waves, they only reach the superficial regions of the brain. Here's the hippocampus down here. But his temporal interference method reaches deeper. Problem with reading is there's a place. Okay. So what he's doing is applying two high-frequency sine waves to electrodes on the skull, and the temporal interference pattern happens in between the two sine waves, and it penetrates deep enough to affect the hippocampus. The frequencies are separated by about 5 hertz, so that the beat frequency that occurs in between those two electrodes is about the same frequency as the theta frequency. Here's the records for one trial for standard stimulation in A and temporal interference stimulation in B. In both A for sine waves and B for temporal interference, the top trace is a stimulus. In each part, the hippocampal recording is the second trace, where you see the raw theta recorded before, during, and after the stimulus. The third trace is a graph of theta frequency amplitude in that recording, and the bottom part is a spectrogram that shows the response as a function of time and frequency. The frequency is across on the y-axis here is about 1 to 40 hertz. The standard stimulus in A increases the theta during the stimulus here, but it goes back to the way it was originally before the stimulus, when the stimulus is turned off. The temporal, it's likely that that increase in the intensity of the theta during the stimulus is just an artifact because the sine wave stimulus itself produces a voltage that looks like theta that gets into the recording. In B, we've got the beat frequency here at the top, and it's rectified. I got too many buttons. Rectified and smoothed by the channels and the membrane of the neuron, so that that intracellular signal might look something like this. And what you see as a result is that the theta increases during the stimulus, and that increase in theta, there's no theta stimulation really. This is very high frequencies, 3,000 hertz, so 3,005. But the theta continues after the stimulus is turned off. These are spectrograms that show, they're averaged over many stimulus presentations, and they show the dose-response effects. Amplitude increases depending on the strength of the stimulus, and the persistence of the theta is clear after the medium and high intensity stimulation, but not after the temporal interference stimulation, but not after the sine wave stimulation. The enhancement, thank you. That is inexpensive, non-invasive method of transcranial electrical stimulation has potential for improving learning and memory functions and even reducing the probability of seizures, since there is that previously mentioned generalized hippocampal formation inhibition during theta. Thank you.